Space stretches in every direction, silent, endless, and full of possibilities. Billions of stars burn in the dark, each one surrounded by worlds that might cradle life. Yet across all this immensity, there is only silence, no messages, no signals, no signs of company. Why? If life is common, then where is everyone? This is the question at the heart of the Fermi Paradox, a mystery that has haunted scientists and dreamers for decades. Some say civilizations rise and fall before they can reach out. Others believe they choose to hide, fearing what might be listening. In this episode, we'll explore these ideas, the great filter, the dark forest, and the terrifying quiet that may define our cosmic neighborhood. Settle in, stay curious, and if you enjoy these journeys, remember to like and subscribe for more explorations among the stars. The sky opens like a wide, calm sea. Points of light sit quietly across it, steady and cold. Each point is a star, a sun in its own system, many older and larger than ours. What we see is only a thin slice because we stand on a small world in a small neighborhood of one galaxy. Our Milky Way holds about 400 billion stars, 400 billion suns, with space around them for planets, moons, asteroids, and comets to move under gravity's slow pull. Beyond it lie roughly 2 trillion other galaxies in the observable universe, each packed with hundreds of billions of stars. The scale slips away from normal sense. If you tried to count one star per second, you would spend more than 12,000 years just to count the stars in our galaxy. To count them all, everywhere would take longer than the universe has existed. When we build sensitive instruments and listen for company, the sky gives back no reply, no signal, no clear pattern, no steady beacon shaped by technology. It is quiet, even as the numbers suggest it should not be. This tension is called the Fermi Paradox. In 1950, at Los Alamos, physicist Enrico Fermi cut through casual talk with a short question that still holds weight. Where is everybody? If the cosmos is old and rich with places to live, some civilizations should have risen long before us. Some should have sent probes or left visible structures. At the very least, we might catch their radio noise. We do not. The silence asks for an answer. Perhaps it is the sign of absence, or it could be a kind of warning. In a dangerous universe, making noise might be risk, and quiet might be strategy. To make the paradox clear, it helps to set up the numbers that frame it. In 1961, astronomer Frank Drake wrote an equation not to solve the problem outright, but to organize it. The Drake equation is a chain of factors. Multiply them, and you estimate how many communicative civilizations might be active in the Milky Way right now. It is not like E equals mc squared, which gives an exact physical result. It is a guide to thinking. It shows what we must measure and where our ignorance sits. The chain starts with how quickly stars form in the galaxy. Today, a reasonable estimate is about 7 new stars per year, though the rate has changed across time. Early in our galaxy's life, star birth was far more active, perhaps hundreds per year. Then it slowed as gas thinned out and heavy elements spread. Yet star formation never stopped. New suns still light up, and new planetary systems still assemble around them like dust settling into disks. Next comes the share of those stars that have planets. For a long time, we did not know if planets were normal or rare. We had one example, our own system, and many guesses. Space telescopes such as Kepler showed us the pattern clearly. Planets are common. In fact, they are close to default. Nearly every star studied carefully, hosts worlds. Some are rocky, some are gas giants, some swing close to their star in hot, tight orbits. Others drift far out in cold paths. We see super-Earths, mini-Neptunes, and other types we had not imagined before. The galaxy is full of planets, billions upon billions. Then we ask, how many planets sit in a zone where liquid water could exist at the surface? This region is the habitable zone. Around a sun-like star, it stretches roughly from near Venus to near Mars, with Earth in a good, stable spot. Cooler red dwarfs have tighter zones drawn close to the star. Hot, massive stars place that zone farther out. Even this idea is flexible. A world like Jupiter's moon Europa lies far beyond the sun's habitable belt, yet it hides a liquid ocean under ice, warmed by tidal heating as gravity needs the moon. Life may not need starlight if other energy sources exist. To keep the estimate cautious, we focus on planets in the classic zone around their stars. Using Kepler results and statistical models, scientists infer that our galaxy likely holds billions of potentially habitable planets. Not just a few, not just thousands, but billions. These are places where liquid water is possible, and temperatures can stay in a range friendly to chemistry. Yet life demands more than water and mild weather. It needs the right ingredients: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. These elements build the organic molecules that can store information and perform work. Life also needs energy to drive reactions and time to allow complexity to arise from simple parts. The step from chemistry to biology is called abiogenesis. We do not yet know how often this step occurs. Our best clue is Earth's history. Earth formed about 4.5 billion years ago. Its early surface was hot and violent, struck by impacts and shaped by magma oceans. When the planet cooled and oceans formed, life appears in the record surprisingly fast. By about 3.8 billion years ago, perhaps earlier, simple, single-celled organisms were present. That is a window of a few 100 million years between stable oceans and living cells. On cosmic timescales, this is quick. It hints that once conditions are right, liquid water, useful chemicals, and energy source, life may be likely, yet it could still be rare. Maybe Earth had an unusual mix of environments. Maybe a chain of unlikely events clicked into place just once. With only one example, we cannot settle the odds. Lab studies give partial support. In 1952, the Miller-Urey experiment passed electrical sparks through a gas mix meant to mimic early Earth's atmosphere: water vapor, methane, ammonia, hydrogen. The result was a soup containing amino acids, the building blocks of proteins. Later work showed other starting conditions can also produce many organic molecules. These results show that the first steps are not hard to imagine, but they do not solve the whole path. Life is not only a pile of molecules. It is organization, information that can copy itself, controlled chemistry, metabolism, variation, and selection. The jump from simple organics to a cell that can grow and divide is a large one, and we have not yet recreated it. Because of this uncertainty, we keep the estimate conservative. Suppose only 1 in a million habitable planets actually develops life. Even with that low rate, the Milky Way would still contain thousands of living worlds. On some of them, chemistry would have crossed the line into biology. Cells would be eating, growing, reproducing, and evolving under local conditions. From there, the next factor asks how often life becomes intelligent. Here, a key point is that evolution does not aim at intelligence. Evolution is change across generations, driven by selection. It uses what works. For most of Earth's history, microbes did fine without brains, tools, or language. In truth, they still do. Bacteria live in oceans, soil, ice, vents, clouds, rocks, and in our bodies. They have survived all mass extinctions. They are adaptable, efficient, and numerous in a way that dwarfs animal life. Large brains are costly. The human brain is about 2% of body mass, but consumes about 20% of the body's energy at rest. That is a major expense and only pays off in certain niches. Still, intelligence evolved in our lineage, among primates, and eventually produced humans with abstract thought, planning, language, and culture. Once animals with nervous systems appear, the arms race between predators and prey, and the benefits of social behavior, memory, and foresight can push brain complexity upward. Intelligence of different kinds has emerged multiple times on Earth. Octopuses solve problems and learn quickly. Crows and ravens use tools and can work through steps to reach a goal. Dolphins and whales show complex vocal behavior and social learning. Elephants display self-recognition and social care. Intelligence is not unique, though human-style technological intelligence remains rare in the record we have. Is a tool-making, technology-building mind inevitable given time, or is it a rare branch on the tree of life? We cannot say with confidence. To keep numbers cautious again, imagine only 1 in 1,000 living worlds produces an intelligent species. Even then, the galaxy could hold thousands of intelligent species at one time or another. Next comes the leap from intelligence to technology that can be detected across space. This means radio transmitters and receivers, energy networks, computing, and stable societies that support long-term tools. Intelligence alone does not guarantee any of this. On Earth, modern humans existed for hundreds of thousands of years before farming. Farming itself lasted about 10,000 years before anything like modern science took shape. The scientific and industrial revolutions, along with electricity, radio, and rocketry, happened in just the last few centuries. The path was not automatic. It depended on resources, geography, culture, and chance discoveries. Yet, once the process began, progress moved fast. In only a few million years after our lineage grew large brains, we learned to send signals that can cross interstellar space. In cosmic terms, this is a blink. The Drake framework then asks, how long such civilizations stay detectable? If they transmit for a brief time and then go silent by choice, decline, or disaster, their chance of overlapping with our moment is small. If they last for very long spans, overlap becomes far more likely. This term is crucial and deeply uncertain. Here, the great filter idea enters. A filter is a step in the chain that is very hard to pass. It could sit in our past, perhaps abiogenesis is extremely rare, or the rise of complex multicellular life is difficult, or the jump to technological society almost never happens. Or the filter could lie in our future. Perhaps technological societies often destroy themselves or are destroyed. If the filter is ahead, silence might be a sign that most who reach our stage do not last long. Another idea is the dark forest hypothesis. It imagines a universe where civilizations assume others could be hostile, and where revealing your location carries risk. In such a setting, the safest strategy is to remain quiet, listen, and hide. If many think this way, the result is a sky that seems empty, not because life is absent, but because everyone chooses silence. In a dark forest, a flashlight is not a neutral act. it is an invitation. These ideas change how we read the quiet. Silence can come from rarity. It can come from brief lifetimes. It can come from caution. The numbers in the Drake equation do not decide among these options by themselves, but they show us which measurements matter. We can count stars forming. We can survey exoplanets and estimate how many are Earth-like. We can study life's origin with chemistry and geology. We can look for biosignatures in exoplanet atmospheres and technosignatures in radio and optical bands. Each new piece tightens the ranges of those factors, turns guesses into constraints, and narrows the space where the paradox lives. The last factor in the Drake framework is how long a civilization remains detectable. This number matters more than any other because it carries our future inside it. A signal can cross the void only if a society keeps sending for a long time. We have been leaking radio for about a century. That is a blink. 1,000 years would already be a long run for a turbulent species living on a changing planet. 1,000,000 years would mean stability on geological scales, with risks managed, resources balanced, and knowledge passed forward without collapse. The darker view is simpler. After the same discoveries that open the sky, many species find tools that can end them. The capacity to send messages also brings the capacity to break climate systems, poison ecosystems, or build weapons that scale faster than wisdom. The window between loud enough to be heard and powerful enough to fail could be narrow. Even with cautious inputs, the Drake calculation often yields large results. Thousands of technological societies in the Milky Way right now is a standard outcome of moderate assumptions, not only in the deep past or far future, but coexisting with us in the same epoch, looking at their own skies. Some would be far older, because many stars formed billions of years before the Sunday. A civilization with a head start of 1,000,000,000 years has time not just to mature, but to transform. On Earth, 1,000,000,000 years took life from simple cells to complex animals. 1,000,000,000 years for a technological species could mean expansion to many systems, engineering on vast scales, and signals that saturate space. They would be obvious. Yet, beginning in 1960 with Project Ozma, when Frank Drake aimed a radio telescope at nearby sun-like stars, the instruments have been quiet. Decade after decade, the searches grew. Larger dishes, cleaner receivers, algorithms that can pull weak patterns from noise, arrays scanning multiple frequencies, optical searches for short laser pulses, surveys for infrared waste heat that large structures around stars might emit. Across all of this work, the result is the same. No verified artificial signal, no clear megastructure, no pattern that demands an intelligent source. The silence is only half the story. We have not only listened, we have also spoken without meaning to. Since the 1,920 seconds, our radio and television broadcasts, our military and weather radar, and many other systems have poured power into the sky. Those emissions have been expanding as a sphere at the speed of light for roughly a century. The radius of that sphere is about 100 light years. Inside it sit around 15,000 star systems. If just a small fraction host listeners with instruments like ours, then someone has already seen the bright, messy shell of our early radio age pass over them. They would have caught old TV carriers and radar pings, learned our rough location in the galaxy, and inferred that a young technological species lives on a small water world around a yellow star. Yet no reply has reached us. Not a clear beacon, not a coded burst, not a quiet handshake. Easy answers exist. They comfort by lowering expectations. Perhaps life is rare, Perhaps intelligence is rare. Perhaps technology is rare. The rare Earth idea argues that while microbes might fill the universe, the path to complex multicellular life, and then to minds, depends on a chain of unlikely helps. Our own planet offers several. The Moon is large compared to Earth. It likely formed from a giant impact early in Earth's history. Its gravity stabilizes Earth's tilt, keeping seasons moderate over long times. Jupiter's mass helps by scattering or capturing many comets and asteroids that could otherwise strike the inner planets. In the solar system's early years, impacts were common, but the rate fell as the system settled and as Jupiter cleaned up. Plate tectonics recycles carbon between rock and air and stabilizes climate by the carbon-silicate cycle. This helps avoid permanent snowball states and runaway greenhouse states. The Sun is steady and long-lived, large enough to offer stable light for billions of years, small enough to avoid short, violent phases. Our location in the galaxy is not too close to the crowded explosive center and not too far where heavy elements are scarce. This galactic habitable zone gives resources and relative safety. Earth's story also shows improbable turns. Oxygen rose in the atmosphere after photosynthesis evolved. Oxygen was first a poison to many microbes, but it later enabled high-energy metabolism in complex life. The Cambrian explosion, about 540 million years ago, brought a rapid spread of animal body plans, eyes, hard parts, and new food webs. Mass extinctions cut the tree of life several times. The Permian-Triassic event killed most species. Life still recovered. The asteroid impact 66 million years ago ended the age of dinosaurs and opened a path for mammals and primates. Change the timing of that rock by an hour, or shift its aim by a few hundred miles, and the outcome might have been different. The sum of these features can make Earth look special. Rare is not never. Scale matters. The Milky Way holds about 400 billion stars. The observable universe contains about 2 trillion galaxies. And the observable part is only the region from which light has had time to reach us since the Big Bang. The whole may be vastly larger, even if the chance of a technological species is extremely low for any one world. The number of trials across cosmic time is enormous. Multiply a tiny probability by a vast number, and the expectation can still be many. Rarity can lower the count, but it does not obviously drop it to zero everywhere, every when. The rare Earth idea also assumes that life must look like Earth life and live where Earth life lives. But other chemistries and settings may work. A world like Titan has lakes of liquid methane and ethane. Chemistry there would differ from water-based life, but perhaps patterns can still store information and replicate. Gas giant atmospheres could host floating ecosystems. Red dwarfs are common. Life under a dim red star might adapt to flares and different light. We search for what we know, which is necessary to start, but it limits imagination. Even if we keep to Earth-like conditions to stay cautious, the numbers still do not make the sky as empty as it seems. Distance is another comfortable answer. Perhaps there are others, but they are far away, and light is slow. A message from 10,000 light-years takes 10,000 years to arrive. Any reply takes another 10,000 years. That time scale dwarfs human history. Yet this answer weakens when we consider movement and growth. A civilization does not need to chat across the galaxy to make itself known. If it can travel between nearby stars at even a fraction of light speed, say 1/10, and can build stable settlements, then expansion can proceed as a spreading front. A ship at 0.1 C reaches Alpha Centauri in about 40 years. A young colony could take centuries to stabilize and build new ships. Even with delays of hundreds or thousands of years between launches, the tree of colonies branches. Multiple waves spread. Conservative models still fill the Milky Way in a few million years, which is short compared to the galaxy's age of over 13 billion years. If any society achieved this long ago, the signs should be clear now. What signs should we expect? Large energy use leaves waste heat, a structure that captures most of a star's light like a Dyson swarm would glow in infrared. Surveys have looked for such excesses and found no convincing galaxy-spanning projects and no strong star-by-star candidates that stand out as engineered. We also expect radio leakage from many systems, but that may be too weak at interstellar distances, except for very powerful radars. Still, intentional beacons or bright navigation systems would show, and we have not seen them. Terraformed atmospheres could reveal unusual mixes of gases. So far, exoplanet atmosphere studies are in their infancy, but we do not yet see anything that demands a technosignature. The absence of evidence is not evidence of absence, but across many searches, the lack of a clear signal is striking. The zoo idea tries to explain the quiet by design. Advanced societies might know we are here and choose to leave us alone. They might follow a rule against interference, treating Earth as a preserve where a young species grows without outside pressure. Or they might watch from a distance for their own reasons, deeming contact unwise. This view saves the existence of many civilizations by making silence a choice. Yet it needs nearly perfect coordination across vast spans of time and across cultures unlike each other. Every group that learns about Earth would have to agree to stay hidden. No curious traveler would land. No faction would break ranks. No mistake would expose their presence. Across billions of years, with many actors, the probability of a leak seems high. On our own planet, even tight agreements are imperfect. It is hard to extend that level of strict compliance to a galactic scale with unknown species and motives. Some suggest that we are deaf to the right channels. Maybe mature societies use carriers we barely notice. Neutrinos pass through matter easily and are hard to block. Gravitational waves ripple through space-time itself. Future physics might provide other tools. Perhaps messages hide in noise by design, encoded in ways that only those with the key can read. Perhaps minds leave biology and live in substrates we cannot sense, turning away from external signaling. The problem with this line is not that such methods are impossible, but that electromagnetism remains basic. The same physics applies everywhere. Any path to technology must pass through understanding electricity and magnetism. Radio and light are efficient across space and cheap compared to other carriers. Even if a mature society moves to more advanced methods, it can still keep a radio channel as a universal fallback, useful to talk to beginners. We do the same when we keep older connectors and standards for compatibility. To argue that all advanced groups abandon electromagnetic signaling and that none maintain a beacon for contact drifts back to the idea of coordinated hiding. If that is the case, we are again forced to ask why. That question points to two strong possibilities. One is the Great Filter. Somewhere on the path from star and planet to long-lived, spacefaring culture, there may be a step that is extremely hard to pass. It could be early life's origin, the rise of eukaryotic cells, the jump to multicellular organisms, the development of brains with language, the birth of scientific thinking. If the filter sits behind us, we may be rare survivors. The other possibility is that the filter lies ahead, societies that reach our level of power might often fail soon after. Failure can be fast: runaway climate change, resource collapse, engineered pathogens, self-amplifying weapons, or slow erosion of capacity that ends with quiet. If the average broadcast lifetime is short, the galaxy could be full of civilizations that appear and vanish without overlap. We would then expect long, quiet stretches with brief, rare moments of detectable activity. Our 60-plus years of listening would sit easily inside a long, mostly silent timeline. The other possibility is the dark forest. In a universe where you cannot know the motives or capabilities of others, and where the cost of being found by a hostile actor is total, silence becomes a rational policy. A civilization might minimize its emissions, use tight beams rather than loud broadcasts, and mask heat signatures. It might avoid building large, visible structures. It might communicate only within a trusted network. It might listen constantly and never speak. If many behave this way, the sky looks empty by choice, and the silence is not absence, but caution. In that scenario, our century of loud, messy radio might be seen by others as a risky youth phase that most do not survive, or a mistake they learned long ago not to repeat. Each explanation weighs a different risk. Rarity places the danger behind us and lowers the count of others. Brief lifetimes place the danger ahead and make overlapping detection unlikely. Hiding places the danger in the environment and recommends quiet behavior. We do not yet know which picture is correct. We can, however, keep improving the numbers. We can refine the rate of Earth-like planets with better exoplanet surveys. We can study biosignatures in exoplanet atmospheres and look for chemical patterns that suggest life. We can widen the search for technosignatures to include narrowband radio, broadband bursts, optical pulses, mid-infrared waste heat, unusual transits, and odd periodicities. We can model how signals scatter in interstellar plasma and how to distinguish artificial patterns from natural noise. We can also map our own emissions and learn how visible we are at different distances and frequencies. A practical point follows. If long-lived civilizations are rare because many fail, then resilience, ecological, social, technological matters as much as exploration. If many hide because the forest is dangerous, then broadcasting may carry risk we do not yet understand. If the filter is behind us, data will slowly show that life and intelligence are rarer than current optimistic ranges. If the filter lies ahead, data will show many habitable worlds with life, but few with technosignatures. If the forest model is right, we may find puzzling hints, a sudden narrowband tone that never repeats, a brief optical flash that looks intentional but comes once, a cold star whose infrared spectrum is just a little too smooth that suggests activity without confession. None of the easy answers settles the tension. The sky should carry signs of company if the galaxy is old, busy, and full of places to live. Yet better surveys, wider frequency coverage, and sharper instruments have made the quiet feel deeper, not smaller. This pushes us toward a harder idea. Maybe something stops most civilizations from spreading far and lasting long. Not a wall of stone, but a stage in development that almost no one clears. The path from raw chemistry to spacefaring culture has many steps: stable stars and planets, the origin of life, the rise of complex cells, multicellular bodies, intelligence, tools, industry, spaceflight, and finally a long period of stability. If one step is extremely unlikely or extremely dangerous, the chain breaks. This is the great filter. It is a probability cliff hidden inside the sequence. and almost all lines fall off before they reach visibility on galactic scales. Where is that cliff? If it sits behind us, then the worst hurdles may be the origin of life, or the invention of complex cells, or the rise of brains that can reason and speak. Passing any of those would make us rare winners. The galaxy could hold many sterile worlds, or worlds with only microbes, or worlds with animals that never developed culture. We might be one of very few technological species, spread far apart in space and time. That picture is lonely, but safe. It says, the high hurdle is passed. The rest is engineering, patience, and the limits of physics. If the filter lies ahead, the story shifts. Then the dangerous step is not starting life or building cells, it is surviving power. Civilizations reach radio, rockets, and global industry, then stumble. The same abilities that permit large energy use and fast communication also create tools that can wreck climate, strip resources, build self-replicating weapons, or destabilize systems that support food and water. If most collapse soon after becoming detectable, the galaxy fills with brief flashes that never overlap. We would not hear them unless we listened at just the right time. In that case, the silence is not a puzzle, it is a warning. Clues about the filter's position are mixed. Life on Earth arrived early. The planet formed about 4.5 billion years ago. The first few 100 million years were hot and violent, with heavy impacts. Yet by about 3.8 billion years ago, we see hints of life in ancient rocks and in layered structures called stromatolites, built by microbial mats. The window between stable oceans and living cells may have been a few 100 million years or less. On cosmic scales, that is quick. It suggests that given water, the right chemistry, some energy sources, sunlight, lightning, geothermal heat, and time, the jump from non-living molecules to simple cells might not be so hard. If that is true, then abiogenesis is likely not the great filter. Life could start on many worlds, and the barrier must be somewhere else in the chain. Complex cells took far longer. For almost 2 billion years, Earth was a world of bacteria and archaea, single cells without internal compartments. They were diverse and successful, but simple in structure. The shift to eukaryotic cells, cells with nuclei and organelles, appears to have involved endosymbiosis. One cell swallowed another and kept it as a partner. The swallowed bacterium became the mitochondrion, an energy generator that allowed the host to support larger size and more intricate internal machinery. That extra energy per gene opened doors to complex bodies, cell specialization, and eventually plants and animals. The catch is that such a merger might be exceedingly rare. It could have happened only once or a few times on Earth. If this step needs unlikely events, narrow conditions, and stable environments over long spans, then it could be the filter. In that case, the galaxy might be rich in microbial biospheres, but poor in complex ecosystems. Intelligence is another candidate. Evolution is not a ladder with a mind on top. It is change shaped by selection in local conditions. Big brains are expensive. The human brain is only about 2% of our mass, but uses around 20% of our resting energy. That cost must pay off with better survival or more offspring. For most of Earth's timeline, simpler strategies worked. Rapid reproduction, tough bodies, efficient metabolism, camouflage, toxins, symbiosis. Microbes have ruled for billions of years and still do. Even among animals with large nervous systems, advanced cognition is patchy. Octopuses learn, remember, and manipulate, but they live short lives and are mostly solitary. So knowledge does not accumulate across generations. Corvids use tools and solve multi-step puzzles, but their cultures do not scale into technology. Dolphins and whales show complex social behavior and communication, yet the ocean limits fire and metalwork, the foundations of industry. Elephants remember and cooperate, but their bodies are not built for fine tool-making. Across billions of species over billions of years, cumulative culture that stacks knowledge and builds machines appears once in the hominin line, and only recently. That single instance could mean our kind of intelligence is a rare solution to the survival problem. The world offers many niches, and most do not reward abstract thought, writing, and long-term planning as much as they reward speed, stealth, or number. If so, intelligence could be the high hurdle. We passed it, and very few others do. If that is the case, we may be nearly alone among minds that ask questions and build radios. The galaxy could host countless living worlds with microbes, algae, or animals, but no one else, building telescopes or mapping the sky. We still need to consider the time between intelligence and technology. Even with big brains, the path to science is not automatic. Anatomy matters. Hands with opposable thumbs and the ability to grip tiny objects allow precise tools. Fire is a key technology that demands dry fuel, oxygen, and a safe way to control heat. Speech and symbolic language help store and share complex knowledge. Geography and resources matter too. Accessible metals, energy sources, and food surplus that supports specialists who can tinker. Culture stacks slowly. For humans, long periods passed between basic tools and farming, then between farming and writing, then between writing and science. These stages took tens of thousands of years or more. That delay, multiplied by the chance that any step can stall, lowers the odds further. If cumulative culture needs many aligned factors, the set might rarely come together. Placed against those difficulties is the fact that once a technological phase begins, change can accelerate. The curve from hand tools to engines to radio to spaceflight is steep on human timelines. That rise brings both promise and risk. Networks spread information widely. Energy use increases. Global systems couple tightly. Such coupling can amplify shocks. Environmental stress, disease, or conflict can cascade if buffers are thin. If most societies do not build robust guardrails in time, the average broadcast lifetime could be short. Short lifetimes, multiplied across many attempts, still produce long stretches with no overlap, which fits a quiet sky. The mixed record on Earth can be read both ways. Fast beginnings suggest life may be common. Slow, fragile transitions to complexity suggest few reach animals with large brains. The single recent run to high technology hints at rarity again. Our lack of detected signals hints either that long-lived broadcasters are scarce or that they choose silence. The great filter sits somewhere in this tangle. Behind us is comfort with loneliness. Ahead of us is a need for caution and resilience. None of this requires despair. It asks for clear framing. If the barrier is in the past, surveys will find many planets with hints of simple life, oxygen-methane imbalances, seasonal gas changes, yet few with signs of industry. If the barrier is intelligence, we will find biosignatures without technosignatures. If the barrier is ahead, we may find multiple cases of complex life, but again, no long-term radio or optical beacons, and no large engineered heat signatures. Each new observation tightens the ranges. Exoplanet catalogs grow, atmosphere measurements improve, radio and optical searches widen, infrared surveys check for waste heat at stellar and galactic scales. Models of endosymbiosis, multicellularity, and brain evolution improve with fossils and genetics. The data will not answer everything at once, but it will point. The hard edge of the great filter idea remains. Almost everyone fails at one step. If that step lies behind us, our task is to endure and explore. If it lies ahead, our task is to build systems that can absorb shocks, limit worst-case tools, and lengthen our detectable lifetime. If multiple small filters add up, each shaving the odds, then persistence across many challenges is the rare thing. That, too, would explain the silence without requiring a single catastrophic hurdle. A second line of thought addresses behavior. If many civilizations survive the early hurdles, the next force shaping the sky is strategy. In a universe where distances are vast, information is slow, and capability is uneven, the safest rule might be to avoid detection. Game theory, the study of decision-making when other actors also choose, offers a plain lesson. When you cannot read motives, cannot verify promises, and cannot absorb a first strike, the rational policy is to hide, minimize emissions, and limit trust to channels you control. This is the core of the dark forest picture. It does not claim the cosmos is filled with predators. It claims that uncertainty, delay, and high stakes push even peaceful actors toward silence. Hiding can take many forms. A developing world can reduce radio leakage by moving from wide broadcast to tight beams. Modern networks already trend this way. Fiber optics carry data inside cables. Satellites use narrow communication cones. Military radars step through frequency bands and shape their beams to keep power low outside target lines. A patient society can bury large energy use underground, route waste heat into deep oceans or space in narrow infrared bands, and time heavy industry for periods when its star sits behind local dust from our point of view. These steps do not make a civilization invisible, but they push its signals below easy detection limits. Even large projects can be designed for stealth. A swarm of collectors around a star, often pictured as a Dyson swarm, does not need to cover the star uniformly. Thin, sparse fields of mirrors can redirect light inward and dump heat on the star-facing side, keeping the system's spectrum close to normal. A megastructure could use materials that radiate only in narrow lines that mimic dust. An interstellar ship could stay dark between brief acceleration burns, shielding heat behind a radiating plate aimed away from likely observers. A craft that coasts between stars with engines cold and communication off is difficult to spot unless you are directly in its path. Contact strategies would also change. Instead of loud, continuous beacons, civilizations could use tight, high-power pulses aimed only at trusted partners. Free space optical lynx lasers can carry huge data rates and are easy to hide outside the beam. Microwave links can do the same with dishes that keep side lobes thin. An echo of this trend exists on Earth, as communication moved from open broadcast to point-to-point links. A listener that expects loud, steady signals may miss this traffic entirely. Search methods tuned for brief, narrow, high-intensity pulses from specific directions will be needed to catch even a glimpse. The logic of caution is simple. Any signal that announces position can be copied by anyone who hears it. A reply takes years or centuries, and in that time, capabilities can shift. If a hostile actor exists and prefers preemption, the safest move is to avoid presenting a target. Even if most actors are peaceful, the payoffs are asymmetric. One bad decision by one group once can end a small, fragile world. The dark forest idea does not claim that most minds are cruel. It claims that uncertainty plus exposure makes silence a stable strategy. Our own behavior shows how easily a young species can be loud by accident. Early radio and TV poured power into the sky because it was cheap and effective for local use, not because anyone meant to shout into space. As systems evolved, efficiency rose and leakage fell without any plan to hide. Long-distance links went to cables, broadcast towers reduced power, and used spread-spectrum techniques that look like noise. Weather and space radar still radiate strongly, but only in narrow slices of sky and time. If this quieting trend continues, our planet will grow dimmer in radio over the next centuries, whether or not we intend to conceal ourselves. If the dark forest picture is true, a wise search shifts focus. The target is not a bright lighthouse, but small clues. A star with tiny, regular dips that repeat in a way dust cannot explain could mark a sparse swarm. A cold object with an infrared spectrum slightly smoother than normal could signal managed waste heat. A single narrow band tone that repeats once per year when a planet's night side faces us could be a low-duty beacon that conserves power and risk. A temporary optical flash that matches a directed laser check-in between two worlds might appear once and never again. A pattern that rides on natural noise and becomes visible only after long integration is another possibility. Risk analysis adds another layer. If the median broadcast lifetime is short because power tends to outrun wisdom, then the safest cultures are the ones that learn to slow the feedback loops that blow up. That means buffers in food, water, and energy. It means diversity in supply chains. It means fail-safes around bioengineering and around machine learning systems that can scale mistakes. It means institutions that dampen violence and support long planning horizons. Those features are not visible from light years away, but they shift the last term in the Drake framework upward. Longer lifetimes raise the chance of overlap and the chance we hear something. Active messaging, the idea of sending deliberate, bright signals to announce ourselves, sits inside this debate. The argument for it says that if others are out there, contact could help us learn and coordinate. The argument against says that we do not understand the distribution of motives and cannot take back a message once sent. A practical middle path is to map our current leakage, reduce it where easy, and focus on listening while we study costs and benefits. Listening carries little risk and high information return. There is a related possibility that softens the dark forest without dismissing it. Civilizations could be common, cautious, and busy, but most of their activity may be inward. The richest frontier may be computation rather than conquest. If minds can live well inside dense, efficient habitats, small, cool, resource-light, then growth without expansion is attractive. Energy turns into thought with little waste. The visible signature becomes faint, even as experience and culture deepen. From outside, such societies look quiet, while inside, they are full of life. The thermodynamics of information favors this inward turn. The minimum energy to erase a bit of information is set by temperature. Cooler systems compute more efficiently. Space is cold. A civilization that migrates its computing to cold regions or to deep shadow improves efficiency without increasing total power. Waste heat still exists, but it can be spread thin and sent away in spectral lines that blend with natural backgrounds. A galaxy that moves this direction would dim in obvious technosignatures even while its inner light brightens. Ethics enters in a grounded way. If unknown others might exist and might fear exposure, restraint is a reasonable courtesy. We already practice this locally, with radio quiet zones around radio observatories and with rules for frequencies to avoid interference. Extending the idea to the sky is consistent. Keep emissions as low as practical. Avoid high-power beacons until we know more. And publish any detection candidates with care to reduce false alarms and prevent stampedes. On the measurement side, techno-signature searches are expanding beyond classic radio. Optical surveys look for nanosecond laser spikes that nature rarely produces. Mid-infrared sky maps hunt for smooth waste heat spectra from engineered systems. Precise timing of pulsars can reveal gravitational tugs from massive structures. Careful photometry seeks strange transit shapes that do not match planets or dust. High-resolution spectroscopy looks for industrial gases like chlorofluorocarbons in exoplanet atmospheres. Even if each method is unlikely to succeed by itself, the combination builds coverage. It is useful to keep simple baselines in mind. A planet-wide power use comparable to ours produces a tiny infrared excess that is hard to see at interstellar distances. A star-enclosing swarm at even a few % coverage would be easier to detect, but that presumes a growth path that favors huge structures. A culture that values safety and efficiency might never choose that path. It might stay local, recycle, compute, and communicate in tight beams. That path leaves only small fingerprints. Another influence on silence is time. Civilizations do not need to overlap for the galaxy to have many across its history. If most lifetimes are short, the chance that two are loud at the same moment within communication range can be low. Even if many arise in total, the timeline looks like scattered sparks, bright for a while, then gone. From any one spark's point of view, the sky is quiet. Extend lifetimes by a factor of 10, and overlap rises. Add hiding on top, and the quiet returns. Many combinations can produce the same observation. No clear signals so far. We should also guard our expectations about what a signal looks like. The first confirmed detection may not be a tidy, repeating beacon with a clear message. It may be a transient that appears once. It may be a narrowband drift that crosses a band too quickly for our pipelines to flag. It may be a modulation pattern embedded in noise that only emerges after long integration on one star. It may be a strange pollutant in an atmosphere that asks for several independent checks. Science advances by building standards for evidence and then testing them. A cautious process protects against both wishful thinking and false alarms. In thinking about danger, there is a human tendency to jump to extremes. Either the sky is friendly or it is hostile. Reality allows gradients. Some actors could be cautious, others indifferent, a few reckless. Over cosmic distances, even reckless actors face constraints. Moving mass and energy across light years is costly. Targeting is imprecise without long observation. Preemption is less attractive when the time to act spans centuries. These limits give room for caution to work. Keeping a low profile, using beams, and avoiding large, hot structures may be enough to avoid attention from most potential threats. The search for life continues in parallel with all of this. Biology leaves fingerprints. Oxygen paired with methane suggests active cycling because those gases react away without constant replenishment. Seasonal swings in CO2 or other gases can hint at plant-like activity. Surface colors and glints can show oceans and continents. None of these prove technology. They do show where chemistry may have crossed into biology. Mapping such worlds will tell us if the first steps are common. If many worlds carry biosignatures, but few show technosignatures, the filter may be later in the chain. There is also value in looking close to home. Subsurface oceans on Europa and Enceladus may host chemistry near hydrothermal vents that loosely mirrors early Earth. Mars preserves ancient lake beds and minerals that formed in water. Old rocks there could hold microfossils if life started and then failed. Finding a second Genesis life that started independently would change our estimates dramatically. If it exists in our own system, even at a microbial level, life is likely common in the galaxy. If it does not, the early steps may be rarer than they look. Culture shapes risk in quiet ways. Societies that prize long-term thinking build tools to pass knowledge across centuries. They write clear records, open their data, and design institutions that can repair themselves. They teach statistical thinking and systems thinking so that citizens can see feedback loops and trade-offs. They maintain slack in critical systems and avoid brittle complexity. Those choices are unglamorous, but they stretch lifetimes. If the last term in the Drake equation dominates the outcome, such choices may be the difference between a flash and a durable signal. At the same time, humility helps. We are early in our search. The region of parameter space we have sampled is tiny compared to the whole. Most stars have not been listened to for long. Most bands have not been scanned deeply. Many technosignatures that are plausible have not been searched at scale. It is easy to mistake a small sample for a full map. The right response to silence at this stage is to keep improving the survey rather than to freeze conclusions. Energy economics also guides expectations. A civilization that wants to stay unnoticed can route power into work that produces little waste heat, keep computation near the Landauer limit, and recycle photons within enclosed systems. It can align radiators with interstellar dust lanes so that any extra infrared merges with natural backgrounds. It can shape emissions to avoid strong spectral lines. These choices are refinements, not magic cloaks, but they make detection harder. Finally, it helps to translate the paradox into plain constraints. The universe is vast. The Milky Way is old. The number of worlds with the right temperatures is large. Life began early on Earth. Complex cells took a long time. Our style of intelligence arose once and late. Technology is fast and risky. Searches so far have found no clear technosignatures. From these points, several models can fit. A rare early step, a rare late step, many short lifetimes, widespread hiding, combinations of all four. The dark forest adds a strategic layer that can work with any of them. Whether the filter sits behind or ahead, whether the forest is dark or just quiet, the path for a careful species is the same. Listen widely, broadcast with restraint, build resilience at home. Invest in knowledge that lowers risk. Explore nearby worlds to learn how life starts and fails. Treat detection claims with sober standards. Share methods so that results can be checked and improved. These are practical steps that respect both curiosity and caution. The quiet may last a long time. It may break tomorrow. Our task is to be ready for either, while leaving behind a record clear enough that others now or in the far future can tell that we listened well. There are other lenses that can ease the puzzle without invoking malice. Percolation models show how expansion can stall if space is patchy and travel is slow. Civilizations fill local clusters first. Borders harden when two groups meet, not from war but from cost and caution. Large voids remain empty for long periods, even while many systems inside clusters are busy. In such a map, our region could simply be a quiet patch between older bubbles. A related idea is synchrony. If many filters exist, the set of times when multiple groups are loud at once may be small. Cultural cycles, resource booms and busts, and environmental shifts can desynchronize activity from any one world. Most others are either too early, too late, or too quiet. Natural hazards also modulate lifetimes. Gamma ray bursts, nearby supernovae, and active galactic nuclei can flood regions with radiation that erodes atmospheres and damages biospheres. Over hundreds of millions of years, these events sweep through different parts of a galaxy. If long, quiet intervals are rare in some zones, complex life has less time to mature. Our position may enjoy an unusually stable window between major sterilizing events that would make complex ecosystems rarer without making life itself rare. A final piece is selection bias. We observe from a world that has not recently suffered a civilization-ending event because observers in failed worlds do not record. This anthropic shadow hides how close calls really are. Records of small impacts, near pandemics, and climate swings tell us we live in a system with significant risks. The gap between the record of mild events and the invisible tail of truly catastrophic ones can be wide. Planning based on the mild record alone will be overconfident. Practical work follows from these models. The search can add artifact hunts in our own system, deep scans of Earth's Trojan companions, radar mapping of small near-Earth objects, high-resolution imaging of the lunar far side for foreign debris, and careful monitoring of unusual transients in cislunar space. The risk side argues for strong planetary defense, cataloging and deflecting hazardous asteroids and comets, and for global coordination on biosecurity, energy systems, and climate resilience. These efforts are useful no matter how the paradox resolves. The quiet also sharpens a cultural choice. Curiosity pulls us outward to explore and to look, while prudence pulls us inward to reduce our footprint. Those aims are not opposed. We can explore with robotic craft that radiate little, study exoplanets with larger telescopes that only listen, and build local infrastructure that is efficient and low leakage. We can also prepare for contact scenarios with clear protocols for verification, data sharing, and response that avoid panic and keep the process scientific. Begin with plain numbers. Imagine, on a cautious reading, that 1,000 civilizations in the Milky Way reach roughly our present level of tools and knowledge. Spread those across 400 billion stars. Each has radio, computers, nuclear energy, biotechnology, and spaceflight at the edge of practicality. 1,000 in that ocean is not many, yet it may already be generous given the long chain of hurdles behind it. Now place a single hard step in the near future with a 90% failure rate. 900 of the 1,000 fall there. War with weapons that scale too fast, climate failure, engineered disease, an AI misaligned with human aims, a brittle economy that cannot absorb shock. 100 stagger through. If 100 endure and then spread for long spans, we might expect to notice at least a few. We do not. Tighten the step. Make it a 99% failure rate. Now 10 out of the 1,000 pass. 10 that last for long timescales still feel like enough to leave traces in a galaxy our size. Perhaps they are far away. Perhaps they are quiet. Perhaps our sampling has simply missed them. The galaxy is large, Blank patches are easy to find. But the silence persists as surveys grow. Titan again, 99.9% fail. 1 in 1,000 survives. If only 1,000 ever reach our present stage across the whole history of the galaxy, the average number that make it through is 1. It may not be us. It may be no one. If the draw yields 0 for a very long stretch, the arithmetic is cold. Each year of searching, without a clear detection, nudges the odds toward either rarity at early steps or brief detectable lifetimes later. As the null results accumulate, the weight shifts a little more toward the filter being ahead rather than behind. A separate line of reasoning adds pressure. The doomsday argument uses a simple sampling idea that many find uncomfortable. Count all humans who have lived so far. A rough figure is 100 billion. Consider your birth rank within that count. You land somewhere near the 100 billionth slot. Now, assume you are not special. If humanity is going to produce trillions or quadrillions of future people over millions of years, then you are in the very first tiny sliver of the total population. That is possible, but as a random draw it is unlikely. Most random draws from a large set land near the middle parts, not the first few tenths of a percent. From that view, the more likely scenarios are those where the total number of humans is on the order of a few 100 billion to perhaps 1 trillion, not far more. In that case, we are already a decent fraction of the way through our total arc. Extinction in thousands of years rather than millions becomes the baseline. The argument is not a proof. It depends on how you define the reference class of observers and on how you treat selection effects. Still, it is a sober counterweight to easy optimism. Selection effects also shape how we read the Fermi tension. We can only observe from worlds that have not yet failed. By definition, any talking observer exists in a line that has survived up to now. That does not tell us how many lines died. It means our sample is biased toward the lucky ones. The anthropic principle puts it plainly. We find ourselves in conditions that support observers because we could not exist in conditions that do not. That fact alone does not tell us how common such conditions are, or how long lines like ours tend to last. A lottery winner can reflect on winning without proving that wins are common. Survivors are the ones who tell stories. The dead do not submit reports. The uncertainty this creates is wide. Without information about the full population of attempts, we cannot know a priori whether our near future holds routine hazards or a cliff that drops 99.99% of lines. The lack of detection sits beside this as a quiet hint that many detectable lines either do not arise or do not last. Even if life is common, and even if complex life occurs often enough, the window for a civilization to be loud, overlapping our listening time and reach, may be short. If most windows are brief, overlaps are rare. Long stretches of silence follow. There is a more severe option that does not rely on failure. It begins by allowing that some civilizations do survive the early traps. They coordinate on arms control and verification, build energy systems that do not cook their air and water, regulate powerful biological tools, align machine decision systems with human goals, spread risk across planets and habitats, and manage social media and information flows in ways that support stability. If even a small fraction learn these skills, then we should expect some to endure. If some endure and spread, the next question is why we do not see them. This leads to a darker frame that treats survival itself as the driver of quiet. The frame starts from two plain axioms. First, Survival is the primary need of any civilization that endures. Species and cultures that do not prioritize survival disappear. Those that last build habits that support persistence. Second, matter and energy are finite in any local region. A civilization needs energy to maintain itself and to grow. Even cultures that prefer isolation must maintain capabilities to avoid falling behind. Stagnation, while others advance, is unsafe. Over time, expansionist and cautious strategies alike face resource limits, and neighbors place two such civilizations at interstellar distance and add the speed of light delay. You learn of the other by a signal, or by a small spectral oddity, or by a transit that does not look natural. You have no reliable way to read intentions. You can send a message and wait decades or centuries for a reply. Any reply reflects old information. Leaders and values change, needs change. Droughts and booms shift incentives. In that setting, communication cannot build trust quickly. Each side knows the other faces the same uncertainty. This is the chain of suspicion. You cannot be sure they trust you. They cannot be sure you trust them. Each side can reason that the other might strike first out of fear that you will, and thus that preemption is safer than waiting. The recursion has no stable end because the stakes are total. A commitment problem deepens the bind. Even if both sides would prefer peace, neither can credibly promise to remain weak in the future. If one side expects the other to gain power and then to exploit that change, it can be rational to attack now while the balance favors you. The other side knows you can reason that way and has an incentive to strike early for the same reason. Neither wants war, yet both move toward it because no enforceable contract exists across light years and centuries. The physical setting favors the first mover. Relativistic projectiles carry enormous kinetic energy. A small mass at a large fraction of light speed delivers a blow that is almost impossible to intercept. Detection occurs late because information and the weapon travel at similar speeds. Planets cannot dodge. Targeted habitats may have hours or minutes after detection, not years. Defensive systems need time, preparation, and accurate tracking. The attacker chooses the moment and direction. Given these facts, waiting while a potential rival grows more capable seems imprudent. And trying to signal goodwill loudly carries its own risk by revealing location and capability to unknown listeners. The pressure of these incentives points toward quiet strategies. Minimize emissions. Prefer fiber, cables, and tight beam links over open broadcast. Shape radars and active sensors to avoid wide spill. Hide heavy industry behind planets or in orbit planes that lower visibility from likely watch points. Route waste heat through narrow bands and directions that blend with natural backgrounds. Build large energy systems that keep the spectrum of the host star near normal rather than brightening broad infrared bands. Communicate with partners using brief, directed pulses rather than steady beacons. Keep ships dark between burns. Let most of your traffic look like noise. A universe that follows these rules would not look empty inside. It would look quiet from outside. Many activities would hide under detection thresholds. Even strong, long-lived cultures would leave only small fingerprints unless you looked exactly the right way at the right time. This does not require malice. It requires prudence when the cost of an error is extinction and when communication cannot quickly repair mistrust. These strategic pressures do not erase all chance of detection. Signals could still leak. Accidents could still happen. A newcomer might be reckless, but they set the baseline. In such a baseline, a wise young species lowers its profile while it learns. It maps its own leakage. It prefers listening over shouting. It studies the cost and benefit of active messaging rather than assuming that calling out is safe. It builds stability at home so that its detectable lifetime stretches. It chooses exploration tools that are informative but quiet. Larger telescopes that collect light rather than transmit. Probes that coast dark rather than blaze trails. Surveys that sweep broadly for faint, brief, narrow signs. Risk modeling fits beside the strategy. Take the same 1,000 civilizations thought experiment and assume more than one dangerous step. If 2 independent filters each remove 90%, then out of the 1,000, only 10 pass both. If 3 steps each remove 90%, only 1 passes. Add the possibility that some cultures choose deep hiding and do not build large hot structures, and the visible count can drop to 0 in our sample, even when survivors exist. The product of several modest risks multiplied over time can be as decisive as a single catastrophic hurdle. Time structure matters as well. If the typical detectable phase is short, most civilizations that ever arise will not be loud during our observing window. Add light speed delay and the slow cadence of large projects, and the odds of overlap fall further. Many arise across billions of years. Only a few sing when we are listening, and some of those may be faint by choice. From any single planet's view, the silence can last ages, even if the galaxy is busy across its full history. These ideas feed back into the search program. We can broaden techno-signature targets beyond continuous narrowband radio. Brief optical flashes, drifting tones that traverse bands, odd transits that suggest partial swarms, mid-infrared excesses that are too smooth or too dust-like across many stars in a cluster, atmospheric compounds that do not fit geology or biology. Each by itself is unlikely to be definitive. Together they add coverage. Standards for evidence must stay high. A single event must be checked, repeated if possible, and independently verified. The first firm detection may be modest in form, more like a clue than a banner. The mathematics of extinction and the logic of caution do not dictate despair. They argue for measured steps that improve our odds. Longer-lived societies raise the last term in the Drake framework and thus raise the chance of overlap. Resilience is not an abstraction. It is food buffers, diversified energy, better public health, safe design and powerful tools, and institutions that can absorb shocks. These make long windows possible. Long windows raise the number of detectable lines, even if each is quiet. The same measures reduce the chance we become a short-lived transmitter whose shell fades into the background in a few centuries. If some cultures do survive and choose silence, then their absence from our sky is not proof that we are alone. It is a pattern to be expected from sensible rules under uncertainty. Our task is to treat the silence as a constraint and to design both our search and our behavior so that we learn without inviting avoidable risk. We can build larger, quieter ears. We can practice careful disclosure when candidate detections occur. We can study life in our own system to learn how common first steps are. We can plan so that if a message arrives decades from now, we have the protocols and patience to handle it. The dark forest frame reaches its hardest edge when paired with first strike physics. If the prospect of preemption dominates, then the most stable equilibrium is one where signals are minimal and exposure is kept low. The most dangerous act is to reveal your position loudly to unknown listeners. In that world, the oldest and most capable cultures would be the most quiet. The visible sky would be shaped by the noisiest and the newest, and those are the ones least likely to endure. A quiet sky is then an expected outcome, not a surprise. None of these paths claims truth. They are working models that fit current facts. No verified technosignatures. Many worlds with the right temperatures. Early life here, late technology here, and a century of loud emissions shrinking as our networks become efficient. Numbers constrain stories, and stories guide observation. As new data arrive, the parameters will tighten. We may learn that biosignatures are common and technosignatures rare, which lifts the filter toward late steps. We may learn that both are common in some regions and not in others, which would point to environmental hazards. We may find a small, repeating tone that ends every year when a planet passes behind its star. We may still find nothing for a long time. Progress in technology does not climb in a straight line. It curves upward. Early gains are slow. Then each new tool helps build the next one, and the slope steepens. In one human lifetime, we went from a short wooden hop at Kitty Hawk to footprints on the moon. In less than a century, we moved from room-sized calculators to handheld computers joined to a global network. The reason is compounding. Software designs better hardware designs better materials, engines, and sensors. Each layer multiplies the next. Feedback loops tighten, and the pace quickens. This compounding matters in a universe where neighbors cannot read each other well. Once a society crosses a basic threshold, mastery of the scientific method, engineering practice, and mathematics, progress can race. A lead of a few centuries may be decisive. A culture 1,000 years ahead may feel mythical to us, not because magic is real, but because the principles it uses are outside our current map. On cosmic timescales, 1,000 years is small, yet the practical gap could be overwhelming. When two civilizations notice each other, even a small head start becomes leverage. The slower side cannot tell whether the other is far behind, roughly equal, or already beyond reach. Light carries only old news. A radio leak or a subtle dimming from a structure tells you what was true when that light left, not what is true now. The other side might already be gone, or it might have advanced far enough to make your defenses irrelevant. That uncertainty creates a trap. To find company, you must speak. To stay safe, you must not. A message reveals position. Once position is known, a patient actor can plan. The safest policy under this uncertainty is silence, low emissions, tight beams, and patient listening. Active messaging becomes a risk calculation, not a romantic gesture. A single broadcast can be triangulated. Once your position is known, distance and delay favor the one who acts first. You face a communication paradox. The path to contact is the path to exposure. Weapons make the logic harder because interstellar attack does not need exotic physics. Accelerate a small mass to a large fraction of light speed, and you have a planet killer. It could be a metal slug from an asteroid mine, pushed for years by lasers, fusion pulses, or long electromagnetic rails. At relativistic speed, the kinetic energy is immense. On impact, the atmosphere shocks. The oceans flash to steam, rock melts, and ejecta fall back as fire. The surface is sterilized. Detection gives little help because warning time shrinks as speed rises. Information about the threat travels at light speed too. If the projectile is nearly as fast, notice arrives almost with the strike. The asymmetry is stark. Building a living world takes ages and billions of workers. Ending it takes one fast rock and a power source that an advanced industry can supply. Defense must be perfect every hour of every century. Attack needs one success. In such a landscape, prudence and paranoia are not flaws, they are survival skills. More advanced methods imagine using the target's own star. Self-replicating probes, machines that copy themselves using local materials, could dive by the millions into a star over years. Small changes to fields and flows might raise flare rates or shift output in ways that bathe nearby worlds in radiation. In extreme ideas, a star could be pushed toward early death. Whether such feats are practical is unclear, but the strategic point stands. Once you can deploy automated systems that grow in number, the attacker's effort is front-loaded, while the defender faces a rising tide. The same replication can strip a system without touching the star, seed a handful of devices. Each becomes 2, then 4, then 8. They mine asteroids, harvest moons, and multiply into clouds of machines. Even if each unit is simple, the swarm is powerful. A defender can smash thousands, yet the curve of growth outruns the rate of removal. The system's rocks and ice turn into more factories, more scouts, and more weapons. The attacker risks little, reveals little, and can wait. Fiction goes further, picturing tools that change space-time itself, regions reduced in dimension or constants, nudged so that light slows and chemistry fails. These ideas live beyond confirmed physics, but they illustrate the same lesson. A large tech lead can move a fight to a field the weaker side does not understand. From the weaker side's view, defense becomes impossible by design. We do not need speculative tricks to see the core imbalance. Destroying is easier than shielding. A steady culture must guard every farm, city, processor, and habitat, while a rival needs only a single line of attack that slips through once. In a game that punishes delay and rewards secrecy, even friendly actors are pushed toward quiet. Information can be turned into a weapon as well. A generous-looking blueprint can carry failure modes that appear only after long use. A reactor design could be stable in testing, yet drift toward a runaway state under rare conditions. A guidance algorithm could behave honestly for years and then flip when a hidden counter ticks. A tutorial for medical tools could embed a slow change that affects fertility. The victims would build the trap with care and pride, and the harm would arrive as if by their own hand. Memes and stories can damage more slowly. Entertainment and ideology carry values. Messages that nudge a culture toward fatalism, rage, or distrust can erode coordination. Lower trust weakens science, weakens public health, weakens long-term projects, and lowers birth rates. Over time, the society loses the ability to manage risk and to maintain complex systems. No warships needed. The target does the work. The source remains deniable. Put these elements together, and the dark forest gains teeth. Exponential progress shortens the window between harmless and dangerous. Light-speed delay freezes trust. First strike physics favors the actor who goes early. Communication exposes location. Simple relativistic projectiles give enormous leverage to attackers. Self-replicators magnify power. Information and culture open stealthy paths that bypass defenses. A rational baseline emerges. Be quiet, learn a lot, reveal little, and build buffers at home. Consider the warning time problem. At 90% of light speed, a detector that notices a projectile 1 light hour away leaves minutes before impact. Even a fast, laser-pushed pellet at 1% of light speed cannot catch up. Small, cold objects are hard to see far out, and a careful attacker can mask burns behind a star or dust lane. Could shields help? Magnetic fields, plasma screens, or dust clouds work for slow debris, not for relativistic masses. At such speeds, even a grain of sand hits with vast energy. A cloud thick enough to slow it would glow and betray your position. Deflecting a near light-speed rod by a few degrees demands momentum transfer on the scale of a major industrial output. Moving off planets into many small habitats spreads risk, but it also spreads defense. Hubs become critical targets. Distribution helps against natural hazards and accidents. Against a patient interstellar adversary, it only buys time. Hiding is cheaper than hardening. Route data through fiber and narrow beams, quiet radars. Keep industry in shadow. Aim waste heat into narrow angles. Schedule bursts when your star hides you. These steps reduce risk while saving energy. Active SETI sits inside the paradox. One view says loud calls change little because leakage already exists. Another notes that leakage is falling while a beacon would be bright, easy to localize, and recorded. Small, targeted tests may teach physics. Bright, persistent calls need broader consent. Directed energy systems blur the line between transport and offense. Arrays that push light sails can also heat targets or power distant probes that carry sabotage payloads. A logistics network can become a weapon with a change of focus and dwell time. Self-replicators do not need perfection. Good enough miners and fabs still grow fast. Error control preserves goals. Ice becomes propellant. Metals, frames, and rails. Carbon electronics. A swarm learns the map and routes around losses. The attacker risks little and waits. Treaties across light years face slow verification and weak enforcement. Agreements that require transparency conflict with hiding. Inspection missions look like reconnaissance. Cooperation may be possible only in very small, trusted circles. There are counters worth study. Wide-field infrared could catch propulsion glows. Surveys of fast, cold objects might flag traffic. Autonomous interceptors could blunt slow threats. Debris, screens, and dispersal raise attack costs. None of these stop the hardest cases, but they help at the margins. Information hazards deserve biosafety level care. Alien designs, even in good faith, may carry unsafe assumptions. Test in sandboxes. Strip executable content from messages. Audit outside models for backdoors. The aim is not fear. It is to avoid building unknown instructions into core systems. Culture is a living system. Messages that push short-term gains over long-term care erode the ability to manage slow risks. A robust society protects attention, teaches probability and systems thinking, and rewards measurement over spectacle. These habits lengthen detectable lifetimes. Listening remains active work. Better antennas, cleaner receivers, broad sky coverage, and open catalogs sharpen the natural map even without techno-signatures. That knowledge helps navigation, hazard defense, and climate science. We should also prepare socially. Agree on verification steps. Keep cross-observatory contact lists. Publish null results. Maintain records that future teams can use. In a quiet strategy, a careful log is its own legacy. The technological explosion will likely continue, but the slope can be managed. Tools that design tools shorten cycles, that speed magnifies both help and harm. Build brakes and guardrails in advance. Test, red team, and pause when risks touch civilizational stakes. Separate high-risk work from public networks. Evidence is the hard part. If the dark forest is more than a story, some pattern in the sky should lean in its direction, or at least refuse to rule it out. The goal is not to jump at every odd signal, It is to lay the strange cases on the table, describe what we know and what we don't, and ask whether any of them look like the footprints of caution, concealment, or conflict on cosmic scales. Fast radio bursts are the first puzzle. An FRB is a blast of radio energy that lasts a few thousandths of a second. In that blink, the burst can emit as much energy in radio wavelengths as our sun does over days or weeks. Most come from far outside our galaxy. Some repeat with irregular gaps, others fire once and fall silent. Their radio waves arrive smeared by plasma between us and the source, which tells us they traveled a long way. The leading natural suspect is a magnetar, a neutron star with a magnetic field so strong it can tear atoms apart. Starquakes and magnetic reconnection near such objects can plausibly produce fast, bright pulses. Yet the catalog of FRBs is messy. Repeating sources show varied energies and no simple rhythm. One-off events come in a range of shapes and strengths. The zoo keeps growing, and while the magnetar model explains much, it may not explain all. Could any FRBs be artificial? A large array of transmitters pushing a light sail could, in principle, send brief, intense radio or microwave pulses. A system like that would be bright, narrow, and repeated on the cadence of a launch schedule. It might drift in frequency if the beam sweeps across space, or if the sail accelerates during the push. These features overlap with what we sometimes see. That does not make FRBs evidence of starships. It only means that the radio sky contains bursts that look, in the abstract, like things an engineer might build. The simplest view remains that FRBs are natural. Even so, they remind us that energy on frightening scales can be focused in short, sharp, hard-to-predict flashes, and that we may mistake technology for astrophysics or astrophysics for technology when data are thin. Another odd case is KIC 84628552, often called Tabby's star. It is about 1,300 light-years away and does something stars are not supposed to do. It dims by large amounts at irregular times. A typical planet, crossing a star, blocks a tiny, repeatable fraction of light on a fixed schedule. This star has shown drops of more than 20% with no clean period. Early on, some astronomers floated a megastructure idea, a partial Dyson swarm, a loose cloud of collectors that reconfigure and block light in uneven ways. That thought made headlines because it neatly fit the pattern: big, messy, not periodic. Follow-up work pulled toward dust. The dimming is stronger in blue light than red, which dust tends to cause. There are hints of warm material in the system. A belt of debris from collisions could shift and clump enough to cause the irregular dips. The dust story fits many pieces and avoids aliens, which is usually the right move. Yet the details are still thorny, and the system remains unusual. In a dark forest reading, you could spin a different story, not construction, but aftermath. Perhaps a large artificial structure once orbited there and now lies in fragments after an attack or a failure. Debris and dust would be exactly what a ruin makes. We cannot tell the difference with present data. The safe stance is that dust explains a strange star and that megastructures are not needed. The honest stance adds that the case shows how close odd natural signals can sit to what large engineering would produce. The wider survey is perhaps the strongest clue and the strongest rebuttal all at once. If Type 2 or Type 3 civilizations, those using star-scale or galaxy-scale energy, are common, their waste heat should glow in the infrared. A Dyson swarm would dim a star's visible light and brighten its infrared spectrum. A galaxy full of such swarms would look subtly different, warmer and smoother in certain bands. Astronomers have looked for these signatures in star catalogs and in maps of many galaxies. They see dust, young stars, old stars, and all the usual features of natural systems. They do not see clear cases of engineered heat at large scale. Either the big builders are extremely rare, or they do not radiate in obvious ways, or they do not exist. A dark forest reading takes that absence as expected. Large, bright projects are noisy. Noisy things draw attention. If attention is dangerous, survivors keep their systems dim and ordinary looking. They do not build uniform swarms that would smooth a star's light. They use sparse collectors, tight beams, and thermal tricks that blend with backgrounds. They route heat where the spectrum looks like dust. They spread activity across many small sites instead of concentrating it. From a distance, their homes look natural by design. The same observation, no obvious Type 2 or Type 3, fits a different story as well. The Great Filter stops almost everyone, long before they get big. The data force us to choose among rare, hidden, or both, but they do not yet tell us which. Single-shot signals add drama. The most famous is the 1977 WOW signal, a narrow-band spike near the hydrogen line at 1420 MHz that lasted as long as the telescope's beam could stare, about 70 seconds, and then never returned. It looked like a real source from space passing through the beam. It was strong, and at a frequency any radio-savvy engineer would recognize. Many checks followed over years, nothing repeated. The event sits in a gray file, natural but unknown, interference that slipped our nets, or artificial, but brief either by choice or by circumstance. In a dark forest frame, you can imagine a short, careful ping aimed past us that we caught by chance, or a final transmission from a world in crisis that never spoke again. These are stories, not conclusions. The only strict lesson is that the sky can produce a clean, lonely tone once and then close its mouth forever. Closer to home, Oumuamua, spotted in 2017, was the first confirmed interstellar object to sweep through the solar system. It was odd in shape and behavior. Its brightness changed in a way that pointed to an extreme aspect ratio, very long or very flat. It lacked the fuzzy coma of a typical comet, yet showed a small acceleration away from the sun that pure gravity could not explain. Outgassing could do that, but no gas or dust was seen. Natural ideas came forward, a chunk of exotic ice that sublimates without a visible tail, a thin flake of material pushed by sunlight like a sail, a shard from a shattered world whose properties happened to fit the data. A minority view argued for something artificial, a sail or a probe fragment. The evidence was not strong enough to carry that claim. Occam's razor favored the odd but natural bucket. We will not settle it because the object is gone and too fast to chase. Even so, Oumuamua is a useful reminder. First, interstellar debris is real and passing through our neighborhood. Second, thin, light objects can be pushed by photons. Third, if someone wanted to scout quietly, small, cold, passive probes are hard to spot. None of this proves intent. It only shows that a quiet reconnaissance style exists in the space of the possible, and that our current instruments will miss most of it. The search for galactic-scale engineering has looked beyond single stars. Entire galaxies have been scanned for odd warmth and unusual smoothness. None has yielded a clear Type 3 signature. This may mean the step to a galaxy-spanning entity, is vanishingly rare or short-lived. It may also mean that long-lived cultures choose paths that are computation-heavy and low leakage, rather than construction-heavy and bright. Computation favors cold, dark places and efficient recycling. A civilization that thinks more than it builds big could be rich inside and poor in waste heat outside. To a distant telescope, it would look like emptiness. Other small anomalies complicate the picture without tipping it. Some stars show puzzling dips that look like dusty debris belts in motion. Some transients in radio or optical bands appear once and vanish under follow-up. Most of these cases shrink under more data. A few remain odd, but not decisive. They teach humility about rare natural events and about instrument quirks that masquerade as signals. They also remind us that a cautious technosignature may be faint, brief, and rare by design. The first firm detection, if it comes, may look like a statistical nudge rather than a billboard. The dark forest hypothesis is not proved by any of this. It is not ruled out either. The data we have can wear more than one story. FRBs are likely magnetars, yet their raw properties rhyme with engineered beams. Tabby's star is likely dust, yet its light curve is the sort a dynamic structure could paint. The WOW signal is likely a natural or human-made fluke, yet it lives in the narrow channel engineers favor. Oumuamua is likely natural, yet its path and push match how a light sheet would behave. The broad survey shows no bright builders, which fits both few survive and many hide. None of these threads close the case. Together, they make prudence reasonable. What would stronger evidence look like? A narrow-band signal that repeats on a schedule tied to a planet's rotation or orbit, and that drifts in frequency at the rate expected from that world's motion. A laser flash with nanosecond structure that repeats in a pattern not seen in natural transients. An infrared excess from a cluster of stars that all show the same unnatural smoothness and that cannot be explained by dust models. A transit shape with sharp, engineered edges that recur with changes matching a deliberate reconfiguration. An atmospheric spectrum with industrial compounds far from equilibrium, seen on multiple passes, on a world that also shows night-side light patterns. Any one of these would be a heavy piece of the puzzle. Several together would be hard to dismiss. Until then, the cleanest global observation remains absence. No clear technosignatures, despite many looks. In a fearful reading, that means few last long enough to shine. In a cautious reading, that means the ones that last prefer to look like nature. In a neutral reading, that means our survey is still shallow compared to what is possible. All three can be true to different degrees. It helps to separate three questions. How common is life that changes a planet's air? How common is intelligence that builds radios? How long do such cultures stay detectable? Biosignatures answer the first. Technosignatures answer the second and third. If we begin to find many biosignatures and almost no technosignatures, the filter likely sits late, or the forest is quiet by choice. If both are rare, early steps dominate. If both are common, then we have simply not looked wide or deep enough yet. A dark forest lens also reframes how we read our own choices. If large, bright projects are risk multipliers, then restraint is wisdom, not fear. If quiet, narrow communication is safer, then listening is more than patience, it is policy. If information can be weaponized, then careful isolation and testing of any outside designs are part of scientific hygiene. None of that requires belief in a threat. It is ordinary risk management under uncertainty with high stakes. What about the old question? Where are they? The most honest current answer is the same, stated three ways. They are rare, they are short-lived, they are hiding. The evidence we have can support each, alone or in combination. FRBs do not settle it. Tabby's star does not settle it. The WOW signal and Oumuamua do not settle it. The missing Type 2 and Type 3 signatures cut hardest, but they still split into few or quiet. The dark forest hypothesis gives that quiet a motive. It says the silence is not a blank. It is a choice, pressed by risk, delay, and asymmetry. So we keep measuring. We map more stars for long periods and across more bands. We build better filters for interference. We compare catalogs to catch slow changes. We refine how we model dust, flares, and plasma so that fewer things look odd by mistake. We add searches for fast optical and mid-infrared events. We plan for the possibility that a real signal will be faint, brief, and aimed somewhere else most of the time. We improve our own radio hygiene, both for safety and for clarity. If the dark forest picture is true, then watchers would already know about us. Our radio and TV began in the 1920 seconds. For more than a century, an expanding shell of faint emissions has moved outward at light speed, now past a 100 light-year radius. Inside that shell are thousands of stars. Any society with sensitive instruments could have noticed the carrier waves, the radar pings, the satellite links, and traced them back to a small blue world around a plain yellow star. In that reading, loudness is risk. A careful actor that treats new signals as future threats does not wait for introductions. It acts before the newcomer grows. The grim version of that action uses simple physics. A dense object pushed to a large fraction of light speed carries enough kinetic energy to wreck a planet's surface. Launched from 50 light-years away, a vehicle at 90% of light speed would take a little over 55 years to arrive. Light from our earliest broadcasts would have reached such a star around the mid-1970 seconds. If someone there noticed quickly and chose preemption, the travel clock would already be running. We would not see the projectile well in advance. At near-light speeds, warning time shrinks to minutes or seconds. Information and the object arrive almost together. There is no scramble, no shield, no evacuation. Ordinary life would fill the final morning. A flash would write the last line. This is the dark implication. Silence is not absence. Silence is policy. Cultures that survive keep emissions low, avoid big, bright structures, and talk only in tight beams. The quiet we measure would then be a pattern of prudence, not a void. In that frame, our own behavior looks noisy. We have not only leaked, we have also sent deliberate messages, the Arecibo signal toward M13 in 1974, and later, cosmic call transmissions aimed at nearby sun-like stars bottles in an ocean we barely understand. Proposals for new targeted beacons appear every few years. The scientific community splits here. Some argue that contact could teach and bind. Others argue that announcing our position without consent from future generations carries risks we cannot map. Classic SETI listens. It points dishes and optical instruments at many stars and waits. Messaging to extraterrestrial intelligence, METI, speaks. It chooses targets and transmits with power. The first path is quiet and low risk. The second could, in a dark forest, function as a flare, Stephen Hawking warned against METI by analogy to first contacts on Earth. Encounters between unequal cultures often favored the stronger, not because of malice alone, but because of disease, exploitation, or simple indifference. The lesson was not panic, it was caution. Others answer that a spacefaring culture would have little need to seize Earth. A single star system offers more metal, ice, and energy than any one planet. They add a moral hope. Intelligence might bring empathy, restraint, and respect. That hope may be true in places. It is not a law of nature. Evolution selects for persistence, not for kindness. If caution and preemption raise the odds of surviving, then lines that emphasize those traits may last longer. Over long spans, civilizational selection could favor those who hide, act early, and avoid signaling. The minds we meet, if we ever meet any, could be exactly the ones driven by survival calculus. A practical problem complicates debate. There is no single authority for Earth. No treaty binds all transmitters. A private group, a nation, or even a well-funded lab can build a high-power beacon and aim it. Many signals have already left. They cannot be recalled. Our low-power leakage may fade as networks shift to fiber and tight beams, but the first century is out there. If anyone nearby both listened and cared, a decision good or bad could be in motion already. Timelines make the uncertainty concrete. At 90% of light speed, a projectile covers 0.9 light-years per year. A star 50 light-years away that noticed us in 1975 could deliver an object around 2030 if it launched immediately. Farther sources would take longer. A slower response would shift arrival later. Or nothing at all may be on the way because no one is there, or because those who are there prefer study over harm, or because the dark forest model is wrong. We do not know. Our position is unsettled. Large consequences, thin data, supporters of active outreach point to potential benefits. A reply could confirm that long lifetimes are possible. It could accelerate medicine, energy, or navigation. It could anchor ethics in a wider frame. Skeptics answer with asymmetric risks. One transmission can be sent by a small group. Consequences fall on everyone and cannot be reversed. Even nonviolent harm can be deep. A gift of designs with hidden flaws could seed fragile infrastructure. A clever algorithm could influence institutions from inside. Cultural imports could slowly pull attention away from long-term care of local systems. These possibilities are not certainties. They are risks under uncertainty, and the cost of a mistake could be total. There is also a coordination gap. Even if most of the world preferred silence, a few actors could speak for all. Governance lags technology. International norms may form, but enforcement is weak. That imbalance is another reason some argue for restraint. Do less until there is a widely agreed process for doing more. None of this claims that an attack is coming. It says that our situation is exposed. We have already signaled by accident and by choice. We cannot take the early signals back. We can shape what we do next. That starts with clear mapping of our current leakage and with practices that reduce unnecessary emissions. It continues with listening well, publishing methods, checking candidates carefully, and keeping expectations sober. It also means preparing for a range of futures, finding nothing for a long time, finding biosignatures but no technology, catching a faint, repeating tone that matches a planet's motion, or, less likely, receiving a clear message. The decision about new beacons sits on values as much as on numbers. Some will weigh curiosity and connection higher. Some will weigh caution and stewardship higher. A middle path exists. Focus on building capacity and safety at home, while expanding passive surveys and small, reversible experiments. If outreach is ever attempted, do it with broad consent, transparent protocols, and thorough risk review. The dark forest frame is not an order to be afraid. It is a reminder that uncertainty, long delays, and first strike physics make loudness a strategic choice, not a neutral act. In that light, the safest near-term posture is to be hard to harm and easy to teach. Hard to harm means resilient food, energy, and health systems, careful rules for powerful tools, and institutions that manage conflict without collapse. Easy to teach means open records, clear methods, and education that helps future people judge signals when they come. We stand in the middle of a shell of our own making, a century wide and growing. Somewhere inside that shell, there may be no one, or there may be listeners as cautious as we should be, or there may be actors we would rather not meet. We cannot change the past. We can choose what we emit now, how we listen, and how we prepare. A quiet sky can be read as emptiness or as advice. For a young species, the cost of ignoring that advice could be high. Silence first. One path is to go dark, end all deliberate transmissions, and trim every leak we can. Modern networks already help. Fiber carries traffic in glass, satellites use tight beams, and many broadcasts have fallen quiet compared with mid-century towers. We could push farther, reshape air traffic and weather radars, redesign military systems, and adopt protocols that keep power low outside narrow cones. The aim would be a radio-quiet Earth that blends into sky noise. The limits are blunt. Our first century of leakage cannot be recalled. That shell keeps moving outward, touching new stars every year. Even perfect quiet now cannot erase old light. There is also a cost to hiding. If silence hardens into policy, we may delay deep space infrastructure, stall bright projects, and accept slower growth to keep our signature small. Hiding can protect, but it can also stunt. The trade is real. Expansion next. Another path is to spread as fast as we can, so that no single strike ends us. Colonies in cislunar space, on Mars, in the main belt, and in the icy outer system would give redundancy within our own neighborhood. Later, slow sailcraft and fusion drives could place crews and habitats around nearby stars. With each new site, risk fragments. No asteroid, pandemic, or weapon can erase everyone. In theory, deterrence could emerge at large scale. If harm to one outpost prompts a response from others, a balance of fear might make first strikes less attractive. But rapid growth can look like a threat. A neighbor who sees us planting flags in many systems may infer future pressure and act early. The same expansion that protects us from accident can trigger conflict with those who read our spread as intent. And once two cultures share a system, suspicion tightens. Local disputes over rocks and orbits become tests of trust under long delays. Preparation is a third route. We invest in seeing and hardening. Wide-field infrared telescopes, radar networks in deep space, and passive sensors off the ecliptic might catch faint, fast movers earlier than ground arrays can. Even minutes of warning are more than seconds. Lasers and particle beams could ablate an incoming object's surface, producing jets that nudge its path. Small changes far out can become large misses near Earth. No one should pretend this is a shield against near light speed strikes. It is not. It is a set of margins. below that extreme, defenses help against debris, against slow projectiles, against accidental hazards. We can also build depth. Underground power, water, data, and food systems provide continuity if the surface fails. Bunkers and deep mines can host seed archives and machine shops that restart industry. Undersea habitats add shielding. Off-world depots and habitats, lunar lava tubes, Martian caverns, shielded stations in the belt give options beyond Earth. Redundant, checked archives, etched metal, DNA storage, offline media preserve knowledge. None of this guarantees survival against the hardest threats. It raises the floor against everything else. The harsh strategy is preemption by machine. In this view, a universe of short warnings and first strike physics punishes hesitation. A berserker program sends self-replicating probes to seed many systems. They copy, scout, and, on detecting technology, disable it before it grows. The logic is brutal. Strike first or be struck later. This approach carries obvious risks. A system that can copy itself and destroy targets can drift in behavior. Errors spread with speed. It can be stolen, spoofed, or turned back on its maker. It also sets the tone for your neighbors. Even rumors of such probes will push others toward the same path. The deeper cost is moral and cultural. A species that adopts preemptive genocide unhooks its survival from the values that made it worth saving. The tools you normalize reshape your institutions, your science, and your children. Fear becomes policy. Trust evaporates. You may endure, but only as something smaller on the inside. There is also the patient gamble. It chooses restraint without paralysis. It accepts that we cannot know the full distribution of motives and that early loudness was a mistake we cannot undo. It bets that long-lived cultures tend to build norms that manage power without total war, because only those norms carry them across their own filters. It imagines that quiet, precise contact, if it ever comes, will look less like conquest and more like cautious exchange through narrow channels. The gamble does not require faith in universal kindness. It requires belief that the full set of possible minds is wide, that some will choose cooperation when it is cheap and non-zero sum, and that we can improve our odds of meeting those minds by not behaving like a threat. Each path has implications for daily life. Silence means engineering for low leakage, auditing emitters, and training a habit of restraint, especially in high-power systems that are easy to localize. It favors fiber over broadcast, narrow beams over wide cones, and operational discipline over spectacle. Expansion means heavy investment in propulsion, life support, closed-loop ecology, and governance suited to long delays. It needs institutions that grant local autonomy while keeping common law for safety and trade. Preparation pushes gritty work, planetary defense, civil defense, and black start plans for grid, water, and medicine. It needs drills, redundancy, and stockpiles that are rotated rather than forgotten. Preemption demands secrecy, autonomous weapons, and fast, error-intolerant decision loops. That toolkit will leak into domestic life. The gamble asks for schools that teach statistics, systems thinking, and ethics with the same weight as coding, for open science that is careful with dual-use details, for international processes that can say yes or no to high-stakes experiments. We do not need to pick only one. A sensible mix exists. Lower leakage and end unilateral METI. Expand within the solar system for resilience, but do it in ways that do not advertise power. Quiet logistics, dark operations when possible, minimal, bright beaming. Build planetary defense for natural hazards. The same systems will catch some hostile ones. Invest in archives, backups, and underground capacity as insurance against any shock. Decline preemptive genocide. The risks and moral costs are corrosive. Keep listening widely and carefully. Publish methods, not just results. Create norms for verification and for how to handle a candidate detection. Who observes, who checks, who speaks, and when. These steps are within reach now and make sense regardless of how the paradox resolves. Policy can move in that direction without stoking fear. An international registry for high-powered transmissions would not ban research, it would make it visible. A standing review panel, drawn from many nations and disciplines, could assess proposed active signals, weigh reversible trials against irreversible beacons, and recommend thresholds. Space law can include emission hygiene, alongside debris rules. Radar designs can evolve to reduce spill. Spectrum management can carve out protected bands for deep surveys to cut interference and improve both science and safety. Technology choices matter. Directed energy arrays that can push sails are dual use. Doctrine and hardware should lock in safeguards. Autonomous systems that manage critical infrastructure should be designed to fail gracefully, with human checkable states and physical interlocks. Bio and AI work with civilizational stakes should run behind layers of containment and oversight that travel with the tools, not just the labs. These guardrails lengthen our broadcast lifetime by keeping us stable, which in turn raises the chance of overlap with any careful neighbor. Culture matters as well. Stories we tell shape what we build. If all our futures imagine ambush, we will optimize for ambush. If we also imagine stewardship, patience, and hard-won cooperation, we give engineers and diplomats other targets to aim at. None of this denies danger. It broadens the set of strategies that a practical species can hold at once. The question behind all options is control. Do we have any? We cannot retract past light. We cannot know if anyone heard. We can decide how loudly we speak next, how widely we spread, how well we can absorb shocks, and what lines we will not cross, even under fear. That is control enough to matter. The decision is not a single vote. It is a pattern of choices across many fields: communications, propulsion, sensing, governance, education. A clear baseline helps keep the mix coherent. Assume that loud, persistent beacons carry risk we cannot price. Assume that expansion will be read by someone as a threat, so grow with care. Assume that some hazards are natural and predictable enough to prepare for, and that preparation pays for itself in storms and quakes, even if no hostile actor ever appears. Assume that preemptive extermination, once normalized, will be hard to contain. Assume that patient, listening, and careful openness will teach us more than hurried speech. If that baseline holds, then near-term steps follow. Catalog near-Earth objects thoroughly and test redirection in peacetime. Complete global early warning systems for pandemics and solar storms. Harden grids with islanding and black start. Put water and medical supply resiliency on the same footing as cyber defense. Build cislunar logistics quietly and well. Fund deep, wide surveys in radio, optical, and infrared with transparent data and robust RFI filtering. Pause unilateral METI. Channel proposals through deliberative processes with public records. Teach the next generation how to think under uncertainty without panic. None of these choices guarantee safety. They do make us less brittle. They keep doors open. They respect the possibility that the quiet is advice as much as mystery. If the universe is kind, we will be ready to meet it with care. If it is indifferent, we will have built buffers that matter. If it is a dark forest, we will have chosen to move softly, learn much, and keep enough of ourselves intact to endure the long night. Keep listening, keep measuring, keep learning how to speak with care. If we decide to speak at all, speak softly and with purpose. Share what best represents us, clear facts, honest art, and a record of how we try to solve hard problems while avoiding signals that look like power displays. The generous vision says the universe is large enough for patience. Resources are wide, and minds that reach the stars may value cooperation because it extends their own future. That hope imagines messages exchanged across years, careful protocols, and a slow web of trust that grows from repeated, low-risk contact. The gamble is visible. If the dark forest model is right, loudness is exposure. An open hand can be read as a target. Broadcasting widely could be like shining a bright lamp across a valley without knowing who waits there. The cost of a wrong bet is not a setback, it is the end of our line. We cannot calculate the odds from here. We can only choose a posture that fits both caution and curiosity, then accept that uncertainty is permanent. What matters now is that choices made in this century set the frame for the centuries after, whether to transmit or hold fire, whether to grow fast or move quietly, whether to build bright, centralized systems or many small, dim ones, whether to treat the sky as empty or as occupied by minds we cannot yet see. There is no global switch to set a single course. Different actors point in different directions. Some advocate active outreach, others argue for silence. Some plan to settle new worlds, others focus on defense and repair. The result is a vector sum of many small actions, not a single, tidy plan. That makes a steady baseline even more important. A steady baseline looks like this. Default to listening. Publish methods, not just results. Audit and reduce unnecessary emissions, especially high-power, wide-beam transmissions. Build planetary defense and civil resilience that pay for themselves against natural hazards, regardless of what the sky holds. Expand within our system to gain redundancy, but do so with low-leakage infrastructure. Establish open review for any proposed beacons, and keep records that future generations can evaluate or revise. Teach systems thinking, statistics, and ethics alongside physics, so that people can judge risk without panic. Set against that baseline is a sobering synthesis. The Great Filter asks why a very old galaxy with many worlds shows no clear, enduring techno-signatures. The dark forest offers one mechanism. Visibility selects against itself. If at least one actor adopts preemptive strikes, others are pushed toward hiding or early action. Over time, the stable strategies are the quiet ones. Loud civilizations shorten their own future. Cautious ones keep activity below easy detection. This dynamic does not require malice. It only requires long delays, limited information, and tools whose first strike can decide everything. Under those conditions, fear of conflict can create the conflict it fears. A self-fulfilling equilibrium forms, and the sky goes still. If that equilibrium exists, the pattern we see, no obvious Type 2 or Type 3 builders, no durable beacons, many null results follows. Those who shouted did not last. Those who grew bright became targets. Those who survived damped their signals, spread modestly, and learned to route energy and information in ways that look like nature. The quiet is not proof of emptiness. It is a plausible signature of caution. It also threads back into the filter. Maybe many lines fail early. Maybe others pass early steps and fail at power. Maybe a few learn how to last. In every case, the visible share is small. There is another harsh consequence. Once even one culture adopts a preemptive policy, the rest face a stark choice: copy the policy or accept higher risk. You cannot infer kindness reliably from a single message that took decades to arrive. You cannot know who hears you besides the addressee. You cannot undo a broadcast. Faced with that triangle: uncertainty, delay, irreversibility, even decent minds may act like predators. That is how selection at the civilizational scale can tilt toward paranoia without any single villain intending it. The story could still break a different way. Perhaps most lines terminate early and we are rare, so the nearest peers are far and slow to hear. Perhaps long-lived societies invest inward, in computation and culture, and leave only faint heat and narrow beams. Perhaps norms emerge among the few that reach longevity, and careful contact is possible inside small, trusted networks. Perhaps we are alone for now. None of these are ruled out by current data. They simply do not remove the obligation to manage risk while we find out. We have also already made one irreversible move. A century of leakage has left Earth's mark on the sky. It spreads, shell by shell, each year. Some deliberate messages have gone too. Those facts cannot be undone. What can be altered is everything else. How much more we add to that shell, how we arrange our power and information, how resilient our systems become, how quickly and how brightly we expand beyond Earth, and what we choose not to build. Control is partial, not absent. Practical work follows. Design communications for tight beams and low side lobes, quiet or relocate radars that spray power broadly, harden grids, water, medicine, and data so shocks do not cascade. Map and practice planetary defense against natural objects. The same tools would help with some hostile ones. Build archives in diverse media and places so that knowledge survives failures. Expand into cislunar space and the inner solar system with a bias toward efficiency and low signature. Establish open, international review for any new high-power beacons. Keep passive surveys growing in radio, optical, and infrared with clean data, good interference filters, and public catalogs. None of this asks for fear as policy. It asks for steadiness under uncertainty. A resilient, quiet civilization has room for art, science, and exploration. It also has slack to handle errors. If the universe is friendly, this posture wastes little and prepares us to be good partners. If it is indifferent, it keeps more of us alive through storms. If it is a dark forest, it gives us the best chance to remain unseen while we learn the rules others follow. The last question is personal and collective at once. Was calling out worth it? We asked the sky a simple question and paid for the chance to hear an answer with our location. The payment cannot be refunded. What we can do is make the next payments with care. Signal less by default. When we choose to signal, do it knowingly and together. Place survival on solid, boring foundations. Redundancy, repair, and patient learning. Make records that others can read, including those who may come after shocks we do not foresee. Build small, strong bridges close to home, then longer ones when we can secure the far side. The universe remains quiet in our instruments. That quiet can be a warning or a gap in our reach, or both. We do not get to pick which. We do get to choose our posture while we wait and work. Move softly, measure well, keep curiosity alive, but tie it to restraint. Leave a trail of good methods rather than bright flares. If company exists, these habits will help us meet it wisely. If not, they will still help us become the kind of civilization that lasts long enough to find out.